What's going on, everyone? In today's session, let's go over what it means to evaluate the limit of a function. Okay, and so conceptually, you can think of finding the limits of a function in terms of what we talked about before, right? So, for example, we know that you're going to see a function in this form much of the time, right? So in this case, we know that y is equal to a function of f of x, and we know that a function, or f of x, represents basically a math equation, right, whose output depends on what value of x you're going to put in. And we've seen from before that an example of a function is f of x is equal to, let's just say, 2x plus 3, right? So this is an example of a function that has a curve that represents this equation, right? And so in this case, you know that depending on whether if you put a small number in for x, say you put in 1, right? The entire function is going to equal, right, 2 times, you're going to evaluate the function at 1, so put in 1 for x plus 3. This is going to give you 5, right? You can do the same thing at a different value. Say we choose a larger number, say we choose 10, right? So the function evaluated at x is equal to 10, right, is evaluated similarly. We're just going to plug in 10 for x, right, plus 3. That's going to give us 23. And you can keep on doing this for many numbers, right? And so let's just use this case, right, to illustrate what we're trying to say. So in this case, you evaluated your function at x is equal to 10. So you can think of it like this. As the limit of x approaches the value of 10, right, for this function that you have, the function value is going to approach 23, or in this case, it's going to equal 23, because f of x you can think of as the math equation that it represents, which is 2x plus 3, right? One more example, just to make sure we have it down before we talk about other things. Let's say I give you the equation of the parabola that we all know and love now, right? So f of x is equal to x squared. Again, this is a function or a math equation whose final answer, right, f of x, depends on what value you input for x, right? So again here, if I put in f of 1 and evaluated x is equal to 1 squared, that's only going to give me 1, right? If I choose a larger number like 10, I'm going to evaluate x is equal to 10. And so this will be 10 squared. It'll be a larger number, okay? And so let's use this as an example to interpret our limit. So in this case, right, the limit as x approaches 10, because that's where we evaluated x, right, the overall value of your function, right, is equal to 100. It approaches 100, okay? And so in these cases, I just want to mention that in these cases, we basically plugged in the x value that we specified down here. But in some cases that we will go over, you don't want to directly plug in right away. You want to look at your function and you want to see if you can factor, right, factor out or group terms that you have, okay? And then this will eliminate chances that you incorrectly evaluate your limit. All right, so with this being said, let's draw a nice line to separate what we just worked on, and then we'll get into this stuff on the left, all this fun stuff. All right, so let's focus on the left side of this line now, right? Let me get my pencil back. And so let's look at plot 1a and plot 1b. Okay, when we're going over limits again, just like we did over here, right? And now we're going to represent it in a plot form. We're trying to evaluate the value of our overall function, f of x, right? And I'll write it here, the overall function value, right? Function value. We're trying to evaluate the overall function value as the value of x, right? As our variable x approaches some number, right? It can approach 1, 2, 3, 4. In this case, let's try to figure out, right, the limit as x approaches positive 2, right? In that case, let's try to evaluate the value of the overall function, okay? Now, if this is the overall curve representing your function f of x, right? We're trying to evaluate the value of the function at this point that we have here. And so you want to look at it, or you want to approach this point from the left, right? And you also want to approach from the right to see if you end up at the same value, or to see if it converges, is what it's called, okay? And so here, you're dealing with a continuous function, meaning your plot is continuous. There's no break, right? There's no gap in the middle. And so as you approach x is equal to positive 2, right, as specified here, when you come from the left, the overall value of f of x is equal to positive 2, right? And as you approach from the right, same thing, it lands on the same point. And so now you can conclude that the limit as x approaches positive 2, right, the overall function is going to also approach 2. Okay, so this is what this looks like in terms of evaluating this point, or the limit, right, as x approaches 2. Now let's look at it for a discontinuous function. And what this means is, and you can probably see it's very evident, that the plot or the curve for your function f of x has a gap or a jump. Basically, it's not continuous and it has a gap somewhere in the middle. So here, same thing. Let's evaluate, in this case, the limit, right, as x approaches, let's do -1. As x, right, these values on the horizontal axis, as x approaches -1, we want to assess the overall value, right? The overall value of our function. And so again, same thing, we want to approach the value that we're looking at, or the value of interest, from the left. And also we want to approach from the right, right, to see if they both converge or land on the same value. All right. And so in this case, when you approach from the left, you're going to land on f of x is equal to 2, right? And then when you approach it from the right, though, when you approach x is equal to -1, right, from the right, the entire f of x function is going to approach -3, right? Because if you draw a straight line here, you're going to get -3. So in this case, you're gonna take this and you're gonna write it in 2 separate statements, right, instead of 1. And the reason why is because as you approach from the left and the right, you're going to get 2 values, or you're going to land on an f of x outcome, right? 2 outcomes that are different. And so that's why you're going to write it 2 different ways. In the continuous case, they both landed on the same value, so you had 1 concluding statement, okay? And so here, let's first do the left-hand side. So now we're going to write for the limit, right, as x approaches -1 from the left. So I'm going to put a minus sign and I'm going to circle it. From the left, the value of my function approaches 2, right? If you draw a straight line here to the f of x axis, right? This is the f of x axis. As you approach from the left, this approaches positive 2. The second statement is the limit as x approaches negative 1 from the right, the value of my overall function approaches, draw a line to the f of x axis, it's going to approach negative 3. Negative 3, okay? So in this case, there's not that much room here, but I would put a box around this. Limit as x approaches negative 1 from the left, f of x approaches positive 2, and I put a box around this. The limit as x approaches negative 1 from the right, the overall f of x function approaches negative 3. Okay, and remember that no breaks, a continuous curve, that means you have a continuous function. Here, you see this jump discontinuity is what it's called, but we'll learn that later. But since there is a gap, to keep it simple, there's a gap in your curve, right? It's discontinuous, okay? And just so remember the difference between continuous and discontinuous functions, right? Because this is kind of how it turns out, right? Approaching from the left and the right might not give you the same value, okay? So with that being said, I just want to touch on a couple of concepts that we're going to need in order to evaluate limits, okay? And so let's move on from 1a and 1b. Let's move on to 2a and 2b, okay? And this is more of a side note or something to really consider in calculus or in mathematics, basically, right? And so in the left-hand side, this is the curve of an exponential function, right? If you've heard of exponential growth, right, or exponential decay, this is the trend that underlies those concepts. So when you talk about investments that exponentially compound, right? If you put in some money and it exponentially compounds, that means it grows really large, really fast, right? So in this case, think of exponential growth, right, as it grows really large, right? And it grows really large really fast, okay, conceptually. And so understand this concept, and then let's look at the concept of a multiple, right? And let's compare the two. In terms of exponential growth, we said that that function is going to grow or decay, right? Really large, really fast in terms of growth, and then it's going to diminish really. It's going to get really small really quickly if you go the other way, okay? When you're considering multiples like this, right, this curve represents a different function. So this represents f of x is equal to 2x, meaning, right, and we know that f of x and y are interchangeable. So these two are the same. So what we're saying here is that the overall value of f of x, right, or the overall value of y, same thing, right, you can write either one, is equal to twice the value of x. So here, if we evaluate x, right, at 2, then y, or f of x, is only going to be 4, right? Because 2 times x is equal to 2 gives you 4, and so that's going to be this point. Very similarly, when you go to x is equal to 3, right? 2 times x at 3 gives you 6. That's going to give you this value up here. And so the thing is, you need to know and remember that exponentials are going to always grow and decay much faster, right, than multiples. Okay, so the reason why I bring this concept up is like this. If I were to give you, right, a function, another function, right, we've been doing a couple now. If I give you the function, let's say x to the 10, right, minus 7x, let's just leave it at that, okay? If I were to tell you to evaluate the limit, right, I wanted you to evaluate the limit as x approaches some really large number, right? So when I say x, as x approaches infinity, infinity is not a specific number, right? In calculus, think of infinity as just the concept of a very large number. So if x is approaching positive infinity, right, what we're saying is x is going to approach some positive, really big number. And if we're saying x approaches negative infinity, all we're saying is x is going to approach some really, really negative large number. Okay? And so in this case, let's say we're trying to evaluate the limit as x approaches positive infinity, and we want to evaluate the value of this function, x to the 10 minus 7x. Okay? And so if you were to look at this, okay, at first glance, it might look like you don't really know the behavior, right? Or you don't really know the value of the function f of x, right, as x gets to such a large value. But if you remember that an exponential function will always grow or decay much, much faster than a multiple function, right, 2x, 3x, 7x in this case, then you'll know that this first term, x to the 10, this thing is going to take off. Basically, if you remember this trend for an exponential function, you're going to know that as x gets really, really large and you raise it to the 10th power, right? In your head, you should be thinking about something like this. It's going to go up super far, super fast, right, in the direction of your positive f of x axis. This is x, right? And then this is going to represent what you think about as x to the 10, right? And so since this value is going to be so large, you can intuitively disregard, right, whatever this value is going to be, 7 times infinity, right? Because this value, let me see here. Give me a quick second. Awesome. And we're back. If you think of commercial break, right? If you think of x to the 10 as blowing up very quickly, as going to get immensely large, then this term is not going to seem as, it's not going to hold as much weight, right? And so in this case, since this term is going to basically dominate, right? This term is going to dominate this overall function as x gets really, really large. This entire function, you can say, is going to approach some very, very large number. And we're going to say that it's going to approach infinity, right? Because remember, infinity is just the concept or idea of a very large number, okay? And this is kind of why I bring this up, okay? And so if you're asking if it's the same the other way, let's just say over here, right? The same way I said that a very, very large number raised to the 10th exponent, right, is going to grow very, very large. You can also ask yourself, if I were to, in basic math terms, try to divide some number, let's say I divide 20, right? Divided by some really, really large number, okay? And let's say, just to keep it in context, let's say I give you a function that looks kind of like this. So let me rewrite this, okay? So let's say I give you a function, right, that looks like 1 over x, okay? There you go. F of x is equal to 1 over x. And I want you to evaluate, right, the same limit. The limit as x approaches some really, really large number, and I want you to tell me what value the overall function is going to approach, okay? And same thing, if the denominator in a fraction is very, very large, right, whatever number or value that is on top, right, is going to eventually get smaller and smaller and smaller, right? Because think of a piece of cake. As you divide a single cake into more and more and more pieces, right, the smaller all the pieces get until you divide it into so many pieces that the pieces are virtually non-existent, right? And so any value, right, divided by infinity, or the concept of a very large number, we're going to say that the value of that function is going to approach 0. Okay? And so go ahead and pause it here and take a second to review what we just went over, if this is a lot of information. And I know this might be a lot of information, okay? So pause the video, go ahead and take a couple seconds, and then after this, we'll jump into evaluating limits, okay? Awesome. So since you are now somewhat comfortable with the concepts that we just went over, let's look at some of the examples that we have, okay? And let's work through them. So we'll start off with a more simple one, right? Very similar to the one that we had before, right? If I gave you this function equal to, I have them right here, just so that, what's it called? Here we go. X over 4, okay? So this is like, I flopped it. So instead of x being at the bottom, like the previous one we did, now it's at the top, okay? So if I gave you this function, and I wanted you to evaluate the limit, right, as x approaches some very, very large number, right? I wanted you to find or evaluate the overall value that the function would approach. And so in this case, whatever this is on top is only divided by 4, okay? And as this gets larger and larger and larger, right, the value is still going to get immensely large. It's not really going to matter that it's divided by 4, right, at some point. Using the same cake example, if you take a cake, right, and you only need 4 pieces out of a given cake, and you keep increasing the size of that cake, the slices are still going to get really large, okay? And so at this point, we are just going to conclude that the function is going to approach a really, really large number, okay? Now, let's use the same function, x over 4, and say I want to evaluate the limit as x approaches 0, right? Opposite end of the spectrum. What value does the overall function approach? Okay, and so in this case, as x approaches 0, for this function specifically, you're just going to insert, right, or input 0 for x, okay? And you're going to see 0 over 4. And at this point, we're going to conclude that the limit as x approaches 0, this overall function is going to approach 0, okay? So these are simple plug and chugs, or you're just going to plug it in and evaluate it. Okay, so now let's look at a different one. Okay, so now let's look at another example, and let's have a function that is going to look a little more involved, but we're going to go over it and make sure that you're ready for whatever, right? Like war ready in terms of calculus. That's kind of lame, but it's okay. Divided by x plus 2. All right, awesome. So if I gave you this function, all right, and I wanted you to evaluate the limit as x approaches -2, okay? And I want you to determine what value the overall function approaches, okay, in this case. Notice that in this case, if you were just to plug in -2 for x, okay, the top would be fine because that's just going to turn out to be some number, hopefully, okay? The main point of what I'm trying to get at is if you were to plug in -2 for the bottom, right, the bottom turns into 0, and essentially anything, right, I'm going to put an A for anything, divided by 0 is going to blow up, okay? And what that means is this is going to approach some very large number, okay? And I'm going to write this out actually, and I'll box it because this is a concept that you need to know. So when you divide anything by 0, okay, that function is going to blow up, okay? And it's going to give you a very large number. And this is not what we want to do in this case, okay? And so here, when you look at the top, right, when you look at this function, you want to take a step back and you want to say, hey, is there anything I can do to make this more simple, right? Is there any factoring that I can do, right? And when you do that, you see this top part and you say, oh, right, 14, how do you get 14? You multiply 2 by 7, okay? Coincidence, 2 plus 7 is equal to 9, right? And so we're going to rewrite the top basically. We're going to factor the top out, okay? And I'll show you what I mean. So it's going to be x plus 2 times x plus 7, okay? And I'll show you why. And all this is over the same thing at the bottom, x plus 2, okay? And I'll show you why right here, okay? And I'll box it in a minute. When you see x plus 2 times x plus 7, you're going to perform something called FOILing, okay? This stands for first, right? You're going to multiply your first terms, x times x, right? You're going to multiply your outer terms, x times 7. You're going to multiply your inner terms, 2 times x. Then you're going to multiply your last terms, 2 times 7, okay? And it's going to look like this. So first, x times x, or x times x, plus my outer, which is x times 7, x times 7, right? Plus my inners, 2 times x, plus 2 times x, right? Plus my last, 2 times 7, plus 2 times 7, okay? And when you work this out, x times x is x squared plus 7x plus 2x plus 14. One more step, combine the 7 and the 2, right? x squared plus 9x plus 14, right? You're going to check that this is what you see up here. So x squared plus 9x plus 14. So now you know that you factored this term correctly. Okay, so this was an aside. Let's mark this as an aside, and you can practice this with other functions, right? So let's get back to what we're doing here. We said we were given this function, right? And we said that if we were just to plug in x is equal to -2, the denominator would become 0. And we know that anything divided by 0 is going to blow up and give you a very large number, okay? And we don't want that. So we took a step back, looked at the top numerator, okay? And we were able to factor it to simplify it. Now that we have it in this form, what you should notice is that x plus 2 is on top and the bottom. So in a fraction, when you have like terms on top and the bottom, you can cancel them out. So this cancels, this cancels. Now you're left with a function that looks like this, x plus 7, right? At this point, now you can evaluate your limit, right? As x approaches -2, right, of your function. And all this means is you can just plug in now. So x plus 7, x is equal to -2 plus 7, and that's going to give you 5, okay? Which will end up being your final answer. And the way we're going to write this, right, is going to be the limit as x approaches -2 for the function f of x, it's going to approach 5, okay? And so take a minute to let that kind of settle in, and then we'll get into our next one, okay? Okay. So let's do another one. This time, here's your function that I'm going to give you, right? The function is going to be x squared minus x minus 30, right? And a big tip, anytime you see like descending powers, right? So x to the 2, x to the 1, right? Because there's a 1 here basically. And then here, technically there's an x to the 0, because anything raised to the 0 power is equal to 1, okay? So anything, right, raised to the 0 power, in your case, right, is going to be 1 for all intents and purposes of this class, okay? So that's another little tidbit for you. So divided by x minus 6, okay? And I want you to evaluate this limit as x approaches 6, okay? So take a second and figure out as x approaches 6, what value does the overall function approach, okay? Now go ahead and pause the video and try it yourself. And after you try, we'll go over it together, okay? Awesome. So again, we were given this function, right? And I wanted you to evaluate this as x approaches 6. I wanted to know what overall value the function approaches, all right? And so the same thing we did with the last one, right? Again, if we were just to plug in 6 into our function, the bottom would become, or the denominator would be 0, right? And we know that anything, right, divided by 0 is going to blow up and give us a very, very large number. And we do not want that, okay? And so here's a second one, okay? So anything raised to the 0 power in this class, that's going to equal 1. anything divided by 0 is going to blow up to a very large number. Okay? So since we do not want to just plug in our x value, right, because that would make everything go pear-shaped, right? We're going to step back and we're going to look at our function and say, can I factor anything? Now, when you see this numerator, right, how do you get 30? You multiply 6 by 5, okay? Between 6 and 5, you can get a 1 by subtracting, right? And so let's just see if we can factor out that top part. So x squared minus x minus 30, the top can actually factor into x minus 6, right? Multiplied by x plus 5. Just by looking at it, you can tell because negative 6 plus 5 is negative 1. Negative x is technically negative 1x, right? So negative x is the same thing as negative 1x because there's only 1x, right? And so if you want to check this, you can FOIL it back out like we did before, right? And let me just finish this up. Okay, and we said that to check this, we can always FOIL, and that stood for multiplying the first x times x. After that, multiplying the outer, right, x times 5. The inner, negative 6, and x. Then the last, negative 6, positive 5. Okay, and so if you wanted to work this out over here, you can, but we're going to continue with this. Okay, and so based on our factoring, again, we see that x minus 6 is a like term, right? So it shows up in our numerator and denominator. So in that case, we can cancel them out because they're the same. And so your function ends up being x plus 5. And at this point, you can just assess, right, the limit as x approaches 6 for x plus 5, right, our function. And when you do that, 6 plus 5 is equal to 11. Okay? And then just to write this out, the limit as x approaches 6, right, the function approaches 11. Okay? And so this was evaluating limits, right, based on functions that were given. And kind of key takeaways, remember, that we got from today was, one, you're not always gonna plug, right? You're not always gonna directly plug your x into your function to get your answer, because it might give you, right? It might give you a 0 in your denominator, and we know that anything divided by 0 for this class is going to blow up to a very, very large number, and we don't want that. So you're always going to look for factoring. Look for factors, right? So you're going to try to break it up into parts that you can hopefully cancel to get a cleaner answer. Okay? And so if you have any questions or comments, leave them below, and I'll get back to you as soon as possible.